So first of all, I'd like to thank you all for coming tonight. What a great crowd, and I apologize for the cramped quarters, but I'm happy everyone was able to squeeze in. My name is Leon Shaptitsky. I'm the Executive Director of the Water in the West program, which is a joint program of the Woods Institute for the Environment and the Lane Center for the American West. At Stanford, the program's purpose is to foster both interdisciplinary research on Western water issues and to connect Stanford researchers through outreach and partnerships with people, managers, and policymakers in the real world. And we're the sponsor of the panel tonight. And we've got three terrific panelists on a difficult and interesting topic. I was trying to figure out how to introduce this topic. So California is facing a severe drought, and it's a historically severe drought. It's the worst drought in recorded human history, at least since the state of California existed. And I was trying to think of how to bring that home, how to impress that on everyone. And that's in part the purpose of the panel, to talk about what we do in the event of a historic drought, what it means to have the worst drought on record, both in terms of how we respond in the short term and how we respond in the long term. So I'll leave most of the numbers to the panelists, but I will say that 2013 was the driest calendar year on record in most parts of California. And the current water year, which is of course measured from November to March as opposed to the calendar year, is currently one of the driest on record. But rather than going into the numbers, as I was sort of looking to figure out how to introduce the panel, I started looking at, there's a terrific website called Aquafornia, which is put on by the Water Education Foundation, which has news and other issues related to water. And it always has 4 or 5 current news stories every day. And I was looking for some statistics, and as I was scrolling down, I kept seeing these unbelievable headlines about the drought. So I thought the way to kick us off would be just to read some of those headlines and sort of illustrate kind of how bad the drought is through news reporting. So one early headline in January said, according to a UC Berkeley professor, "Brace yourself for California's driest winter in 500 years." All right. Another headline from January: California snowpack hits record low. That's from the LA Times at the end of January, and it was reporting that the snowpack at that point was 12% of normal, and on that date, the previous record had been 21% of normal. So it's almost half the previous record. Another headline, this one from the Sacramento Bee: California orders dozens of streams closed to fishing as drought worsens. Another headline: State Water Project will deliver no water this summer. That's from the San Jose Mercury News. No water from the State Water Project. A few weeks later, the news from the federal government was just as bad. Most Central Valley growers to get no water from Central Valley projects. That's from the Los Angeles Times a week or two ago. A headline from Capital Public Radio: officials report that 10 communities are at risk of running out of water in 60 days. That's from last week. I thought this one might be hopeful. Severe drought. California has been here before, a recent headline from the LA Times. But it turns out what they were referring to are tree ring data from the last 1,000 years. So we've been through this before, but not recently. Another headline: California drought threatens coho salmon with extinction, and the water levels are so low in some rivers that there are barriers to salmon migrating out of the rivers to the ocean and migrating into the streams from the ocean. Perhaps the ultimate sign of the drought apocalypse, this from the LA Times last week: Lady Gaga, California's new drought spokeswoman. So we know that the ground is parched. So the drought's different than previous droughts, and I hope tonight the panel can talk about what that means. How much worse is this than previous droughts, and what does it mean for California to be facing the worst drought in our history in terms of both how we get by this year and how we manage our water in the future? And I think we've got a great panel to do that. So our first panelist, who adds a little bit of youthful vigor to the panel, is Daniel Swain, who's a PhD candidate in Stanford's Department of Environmental Earth System Science. And he, through his terrific climate blog, Weather West, coined the term the ridiculously resilient ridge, or now just shortened to triple R or R cubed. What's the
triple R seems to have caught
triple
on.
R has caught on, to refer to the weather phenomenon that was led initially to the cause of the drought. Daniel studies atmospheric processes that connect the Earth's middle latitudes to the equator and polar regions, with a particular emphasis on climate change. Daniel informed me actually today that recently The Economist picked up the term ridiculously resilient ridge, so it's gone worldwide. Our second panelist will be Buzz Thompson, the Paradise Professor of Natural Resources at the Law School and the Perry McCarty Director and Senior Fellow at the Stanford Woods Institute. Buzz is one of the nation's leading experts in natural resources law and water law, and is published widely on both topics, including scholarly articles, textbooks, and publications for broader audiences, one of which I would single out and recommend if you're really interested in this topic and want to take a deep dive. Buzz, along with several other California water experts through the Public Policy Institute of California, published a book called Managing California's Water in 2011, and almost anything I think that comes up tonight is probably covered by that book in some respect. And our final panelist, person who actually has to deal with these problems, is Tom Zichterman, who's the Associate Director of Water Services and Civil Infrastructure at Stanford University. Tom manages the operation of all of Stanford's water supplies, including domestic water, surface water, wastewater, and storm drainage systems, and also chairs the Water Sustainable Working Team at Stanford, which is currently planning the long-term sustainable management of Stanford's water supply and demands. Tom was trained as a civil engineer? Correct. And has been at Stanford for about 15 years. And he'll talk about the implications of the drought for Stanford. I have to say I got a preview of Tom's presentation yesterday in a different setting, and just to give it away a little bit, it turns out that, at least from my perspective, the way Stanford is prepared for the drought, actually, we're actually in really good shape. And so what's interesting is not the crisis that Stanford faces, but the ways that perhaps Stanford could serve as a model for other communities in California. So Daniel, you're up. Oh, and one final thing, just the rules of it. I think the way we're going to handle this is each panelist is going to speak for approximately 15 minutes. They'll just speak in a series, and then when they're done, there'll be an open forum for questions.
Well, first I just want to thank the panel organizers for bringing this together and allowing for this impressive gathering in the room tonight. So it's great to see so many people here and engaged with water and climate issues in California. So what I'm going to talk about tonight, my focus of the talk will be on the meteorological aspects of the ongoing extreme drought in California. So just a very quick outline of what I'll be talking about over the next 15 minutes or so. I'd first like to just give some brief context of the history of drought in California, the kind of precipitation variability that California experiences, and sort of to place the current drought into that kind of context. Then I'll delve into the atmospheric dynamical aspects of the current drought in California and the meteorology underlying this extraordinary dry period. And then I'll have at least a brief discussion of some of the projections for the near-term future and also for the longer term, including what might or might not be going on next winter, which is a topic of considerable interest right now. So drought in California, those of you who have lived in the state for more than a decade or so, I think, are pretty well aware of the fact that drought is not an uncommon aspect of climate in California. There have been about 10 significant drought events in the past century in California, the two most notable of which, the first was the 1976-1977 drought, which was an extreme 2-year drought, and the other one in recent memory is the one that lasted a multi-year drought from the late 1980s through the early 1990s. And there's evidence in the dendrochronological record, that is the tree ring record that was mentioned earlier, of droughts on much longer timescales than this in California's pre-historical period. So here, up on the screen now, I have, this is a time series of annual precipitation in the state of California over a 119-year period, going back to 1895 and including the current calendar year 2013. And the first thing I think you can take away from this is that variability of precipitation in California is quite high, and there are some very high years followed almost immediately by very low years. And this is something, again, that even on, within the time span of human memory, people have a pretty good idea that this is the case. But I thought I'd point out a few remarkable years in California's precipitation history on this plot. The first of those is the 1976-1977 drought that I mentioned earlier, which is sort of the benchmark for short-term extreme droughts in California. The next one is the very heavy precipitation, in fact, the record high in this entire 119-year period associated with the 1982-1983 El Nino event. And a lot of you probably remember that because it resulted in a lot of flooding in Northern California and the Bay Area, and a lot of damage and even loss of life in parts of the state. Another very wet year was associated with the 1997-1998 El Nino event, which also caused considerable damage throughout Northern California. And then finally, I'd like you to direct your attention to the very lower right of the plot, all the way down there, is this year. So that's the 2013-2014 drought, and it's clearly the driest year in the 119-year record, and it's actually the driest by a considerable margin. So this plot shows that same data in a slightly different way. This is a histogram of precipitation in California, essentially showing the distribution of what rainfall looks like over time. And sort of the average precipitation on a statewide basis is about 22 inches. But my main purpose in showing this particular plot is to mention that there are more very wet years than there are very dry years. The distribution of precipitation in California is not symmetrical. And so that has implications for, I think, that we might hear about later, about water management and sort of managing these extreme events, because we expect to see more of one kind than the other. And again, just for context, that's 2013, the lowest in the distribution. So as we've already heard, calendar year 2013 is the driest, or was the driest, in the full 119-year formal record, and probably for a considerably longer period than that. We have direct observations of precipitation for some observation stations like San Francisco going back into the middle 1800s, and this was still the driest year on that record. And as I mentioned, there's some evidence in the tree ring record that it was the driest winter in several hundred years at least. The current water year, which runs from October through the present, the current water year to date, I should say, is also the driest year on record, and it has been for most of the water year thus far. Sierra snowpack has been tracking at record low levels. It briefly got out of the record low territory, but now, as of this evening, it's back into it again after our rain a couple weeks ago. And also inflows into reservoirs, the major reservoirs that supply the water to all of California, most of which are located in the northern half of the state, are also at record low levels as we sit here this evening. And that's sort of reflected by the fact that nearly 70% of California is currently experiencing severe to extreme drought conditions. And this is just a graphical representation of that. You can see at the core of the drought region is centered really in central California, extending from the coast into the San Joaquin Valley, which, as I think we'll also hear about maybe a little bit later, is a very important agricultural region nationally and even internationally. Again, this is another way of looking at that. This is the current departure from normal for the current water year. The red areas are depicting regions where precipitation is below 25% of normal, which is actually most of California, and almost the entire rest of the state is covered by the orange color, which suggests that almost everyone is less than half of where they should be this time of year. So one of the big questions then is, why has it been so dry in California in 2013 and now for the early part of 2014 as well? The short answer is that there's been an extraordinarily persistent region of atmospheric ridging, or high pressure ridging, over the North Pacific Ocean. And what that ridging, which has been coined the ridiculously resilient ridge, a term that's caught on, I think, in the recent weeks, what that's done is essentially deflected the prevailing storm track, which would normally deliver periodic precipitation and storminess to the state of California during the wintertime. Has redirected that storm track well to the north into Alaska and into British Columbia. And so while regions to our north are receiving very heavy precipitation and unusually warm temperatures, California's just sort of been sitting high and dry for the better part of 14 months. What's interesting is that these blocking ridges in the atmosphere are not actually all that unusual in the North Pacific Ocean. They are actually a feature we would expect to see there this time of year, but what's unusual is that this one has lasted for many months. Typically they last anywhere from 1 to 4 weeks, generally not more than a month. And something I'll touch upon very briefly later is the fact that the atmospheric conditions, the very anomalous conditions in California, are actually part of a coherent pattern of anomalies throughout the northern hemisphere this winter that are leading to a whole slew of weather extremes in different regions. So this is sort of a picture of our ridiculously resilient ridge, the triple R. And this is essentially what this picture is depicting is the departure from normal, so the difference between what we observed and what we would expect to see in terms of the geopotential heights, which are sort of this metric of atmospheric temperature over the North Pacific Ocean. This is an annual mean anomaly, which means that this quantity is this huge region in the North Pacific is below normal on a time scale that's pretty unusual. It's very rare to see anomalies persist for 12-month periods like this one. And to give maybe a more intuitive indication of what this ridiculously resilient ridge, the effect it's having on the wind patterns over the same region, the plot on the left shows the departure from normal for the zonal winds, the west to east winds that typically blow over the Pacific Ocean during the winter time. And the purple region suggests where those west to east winds are weaker than they would normally be, and the red suggests where they are stronger than they would normally be. And this is for the current water year since October. And on the right, you can see the similar plot for meridional winds, that is the north-south or the south-north winds. And the regions that are red here, and that's the RRR sort of in between those regions, the regions that are in the red are where we have unusual south to north flow. And the region in the purple is where we have unusual north to south flow. And so what you can sort of see, if I can, let's see, there we go. The circulation around the ridiculously resilient ridge is sort of acting like this. So typically our storms that originate over the Pacific Ocean and sort of come into California generally from the west, moving west to east. But what's what happened this winter is the storm track is sort of going like this instead and going well into the north. And as I mentioned just a little while ago, this pattern is part of a global series of anomalies in the upper atmosphere. And so what we were just talking about, this anomaly over the North Pacific Ocean, is what's leading to the drought in California. But downstream of that, we have another sort of couplet of north-south wind anomalies. And that's associated with the unusually cold and snowy conditions that have been experienced over the Midwest and the eastern seaboard for much of this winter. Also associated with the unusual southward excursion of the so-called polar vortex. If we look even further east over the Atlantic Ocean, going towards Western Europe, we can see yet another one of these north-south wind anomalies, and that's been associated with unusually heavy rainfall and persistent storminess in the United Kingdom, where they've actually experienced record flooding so far this winter. And even a little bit further east from that, yet again, another one of these north-south wind anomalies associated with unusually cold and snowy conditions and along with ice storms in Eastern Europe. So my point here really is this is part of a coherent pattern of anomalies throughout the northern hemisphere this winter. So what does the forecast look like? Well, at least in the short term, there's some good news. It actually looks like it will start to rain tomorrow, which I think may have something to do with the fact that this drought forum is held tonight. That's Murphy's Law of forecasting, I guess. It does actually look like there will be 2 relatively strong storms this week, certainly by the standards of the past 14 months. And so there should be some significant precipitation on the order of a couple inches, pretty uniformly distributed throughout California. So some beneficial rain and snow. But what's important to keep in mind is that this essentially will bring us a week of typical winter weather when we've essentially had 2 winters of very atypically dry and stable conditions. So it's going to take a lot more than 1 week to make a meaningful difference in our very long-standing, very deep rainfall deficit. And so unfortunately, it does look like that some ridging may return later next week. And looking forward, the official Climate Prediction Center forecast does call for increased chances for below normal precipitation for the rest of the water year. Probably not what anyone really wants to hear right now. But there's an interesting question of what might start to occur next winter. There's some interesting developments in the eastern tropical Pacific that I'll try and end this talk with in just a minute or two. So here's just a quick graphical representation of what's been going on, or actually this is a model representation of the storm this week. On the left panel, you can see a region of strong zonal west to east winds coming into California, which is not something that we've seen very often over the past year or so. And a nice deep trough, as we call them, off the coast of California. So that's good news for the week anyway. And over on the right, you can see that there's a few inches of rain headed for California this week. This is sort of the medium-term outlook. For next week, unfortunately, we see something that looks an awful lot like the ridging over the west coast and North Pacific that we've seen recently. And this is just a representation of the Climate Prediction Center forecast calling for below normal precipitation for the next few months. But I think more interesting than that, potentially, as I mentioned, is what's going on in the tropical Eastern Pacific as we speak. What I have up here on the left is a plot. On the vertical axis is depth, and on the horizontal axis is longitude. And essentially what it's showing is a pool in the equatorial Pacific Ocean of very warm water. And so that's originating in the West Pacific, below the surface of the ocean. And as you can see, as this graphic marches forward through time, it starts out in the west, and it's been starting to move a little bit to the east. That's a pretty strong precursor of an El Nino event in the Pacific Ocean. And the departure from normal temperature in this region is actually quite large. 5 degrees Celsius is a big anomaly when you're talking about a mass of water. So what does that mean for the future? Well, the models that we use to predict climate seasonally, including El Nino, are subject to a considerable amount of uncertainty, but right now they are suggesting that sea surface temperatures will increase over the next few months to be above normal in the canonical El Nino region. So what we're seeing right now in our observations of the Eastern Pacific and in the climate model forecast for the next several months leading into next fall are consistent in saying that there's an increased probability of El Nino developing. And the implications that has for California precipitation, especially if it's a strong El Nino event, are significant. And I'd be happy to talk more about those when it's time for questions. And I think those questions will actually have to wait a little while, but I just will close by showing this is a satellite image of the current storm off the coast of California, and that's a very welcome sight. And there hasn't been an interesting satellite picture like this in a long time, so this was taken just a couple hours ago. So I think I'll close with that now, and thank you for listening.
So thanks, Daniel. It's a great privilege to actually be on this particular panel. And if any of you have not visited weatherwest.com, which is Daniel's blog site, I really encourage you to follow it. It's, to me, one of the best websites around. Provides all the information about weather in a way which is both rigorous on the one hand and also totally accessible to somebody who's not an expert like me. I also have to just acknowledge, as Leon pointed out, one of my titles is I'm the Perry L. McCarty Director of the Woods Institute for the Environment. And it's very seldom that I actually have Perry McCarty in the audience here. Professor McCarty really developed the environmental engineering program here at Stanford, and is one of the great scholars in the area of environmental engineering and water. It's risky, however, I have to say, having a title that is named after Professor McCarty, because I've gone to a wide range of talks where it's advertised that me, the Perry L. McCarty director, is going to be there, and then to have people come up after the talk and say, well, they really enjoyed my talk, but they had thought that Professor McCarty was coming to speak, and they were really disappointed to find out that he wasn't there. In addition to that, sort of one other story on this, I have both that title and also I'm the Paradise Professor of Law over in the law school. And I published a book about a year ago on property issues. And when the galleys came back from the publisher, not only did it have my name on it, but it also had Professor McCarty as an author and also Robert Paradise as an author. So there are a lot of people who can't quite figure out why people have those multiple titles. So what I want to talk about this evening is preparing for the drought to come. Because as Daniel pointed out, this drought could end starting tomorrow. It actually looks like we'll be stuck with this for another year. But at some point, this drought is going to end. But the other thing you know from listening to Daniel's talk is that we are going to have more droughts in the future. And so as Californians, we need to be thinking about how are we going to prepare for those droughts that are yet to come. To some degree, the current drought is baked, right? I mean, we have a set of institutions and resources that we are stuck with at the moment that we will deal with the drought as best we can. But the question is, how do we deal with those future droughts? Now, Daniel already pointed out that droughts, of course, have been around since California formed as a landmass. So we actually saw a number of serious droughts in the 19th century. After California became a state, the first major drought was in 1856. And if you think today's drought is bad, not only did they have a severe drought back then, they had an intense summer heat, they had 2 earthquakes, thunder and lightning, according to one book, and severe sandstorms, which is not something which I associate with California today. Or as one author pointed out, it was a climate that, if not pleasing, was at least varied. Then the major drought in the 19th century was this drought of 1862 to 1865. And to show how in California we do have dramatically different weather conditions, this drought actually began with a serious flood of the Sacramento River. And the picture you see up here in the lower left-hand corner is actually a flood of the city of Sacramento. But as soon as the water left the city of Sacramento, we began a 3-year drought period that spelled the end of what was then a major cattle industry in Southern California. As a result of the drought, the cattle industry died off and never recovered. Then, as Daniel pointed out, we've seen a variety of serious droughts during this century. Actually, I guess I'm out of date already. The 20th century. The most serious, as Daniel pointed out, was the 1976-77 drought. This is a picture of Folsom Lake. That's part of the Central Valley Project. It dams up the American River. As you can see from both that picture and this picture, Folsom Lake dried to just a small little puddle during that particular drought period. And again, as Daniel has pointed out, we're in the midst of a even more serious drought today. On the left-hand side here, what I've shown are the current conditions of all of the major reservoirs in California. On the right-hand side over here are the major aqueduct and water projects in the state of California. The major ones that should attract most of Southern California's attention is, first of all, the Central Valley Project, which begins all the way up here with Lake Shasta and then actually distributes water to the eastern side of the San Joaquin Valley. It also has a number of dams like Folsom Dam over on the eastern side of the Sierra. And then the State Water Project, which brings water down from Oroville Dam, again through the Delta and all the way down, then over the mountains into Southern California. If you can see any of these graphs up here, what you'll see is that Shasta Reservoir, one of the major and the beginning reservoir for the Central Valley Project, is right now only about 38% capacity, which is about 50% of its normal capacity. And then Folsom Lake, which I showed you a moment ago, is at about 30% right now, which is again about 50% of capacity. Folsom Lake has dried up to such a degree at this particular point that a town which has not existed since 1955, when Folsom Lake was flooded, Mormon Island, has actually reappeared and is being inundated by archaeologists interested in what happened 50 years ago. If you look at the State Water Project, you can look at Oroville over here, it's at about 39% capacity, again about 50% of normal. And San Luis Reservoir, which is very important not only for Southern California but also for the Santa Clara region, is about 33% capacity, or about 40% of what it would normally be. So how have we traditionally dealt with droughts? And we've gotten through droughts in California quite effectively. Well, one approach that we have followed in the past has been conservation. So the major drought that we faced prior to the current drought, the 1976-77 drought, we got through that primarily through conservation. There were a number of cities in California that actually reduced their water use by about 40%. During that period in order to be able to get through the low water use period. I was actually living in San Francisco at the time and clerking for a federal judge up there. And any of you who lived in this particular area at that point in time know that we were under severe rationing. And in San Francisco, we were only permitted a little bit of water each day, to the degree that the daughter of the judge that I was clerking for was getting married that fall, and in order to be able to have enough water for all of the wedding guests who were coming to that particular event, they used their next door neighbors' bathrooms and took showers in their next door neighbor's house for about 2 months before the wedding actually took place. A similar way in which we have gotten through prior droughts is through water marketing. Urban areas have paid agricultural areas to conserve water, and then taken that water that they have purchased and actually brought it to the urban areas. As probably a number of you know, there are a number of urban areas that actually have dry year options with agricultural areas, where they have paid ahead of time to have those agricultural areas reduce their water use in order to be able to transport it to the cities during dry periods. And if you look at this particular chart up here, what this chart shows, I think probably the most important aspects of it are these bars, and what the bars show is the total amount of water which is transferred through water markets in California in the years that are shown. And then the colors of these years show whether or not we're dealing with a very dry year, normal year, wet year, or very wet. And what you'll see is that our water markets are most active during periods of drought. So for example, in 1991 and 1992, we actually created a state drought water market in which the state of California purchased water from farmers who were willing to give up some water during that period, who were able to conserve or fallow their fields, and then resold that water either to urban areas or to other farmers that needed more water. And so again, you'll see in these very dry years, very active water markets. In these dry years over here again, very active water markets. So that's a second way in which we've gone through our droughts in the past. A third way in which we have gotten through our droughts in the past is by basically saving up our water during the wet years so it's around during the dry years. And this is a picture of Diamond Valley Reservoir. This is one of the most recent reservoirs built in the state of California. It was built by the Metropolitan Water District of Southern California after the last major drought in the state. It actually holds almost 1 million acre-feet of water, which is enough water for, probably about 1.5 to 2 million homes over the course of a year. So by building these reservoirs in Southern California, the Metropolitan Water District has been able to actually stretch the water supplies that it gets during the wet years, make that water available during the dry years. As a result of this, Southern California is actually in much better shape during this drought than they were in prior droughts, and a lot of cities in the Central Valley or in Northern California. And then another way in which we get through drought periods is we turn to groundwater. So we have vast storage of groundwater underneath much of California, and to the degree that your surface streams dry up, one thing you can do is you can turn to the groundwater and you can pump the groundwater, and that's something that we have done during virtually every drought. And then one final way in which we have gone through droughts is we basically borrowed it from the fish. In the same way that farmers generally have to reduce their water supply during dry periods and urban areas do, We also tend to have less environmental water available for fish and wildlife. And in fact, if you look at the data over the last 50 years, the largest hit comes from the environmental water rather than from the urban and agricultural water supplies. That might be different during this drought because we're doing a much better job enforcing the Endangered Species Act. But in prior droughts, fish lost out first. But there are increasing challenges, I think, to all of these traditional methods, and let me just mention a couple of them. First of all, as I suggested earlier, one way in which we've frequently gone through droughts is that we've conserved water. But as we have grown as a state, one of the things that we have done is that we have resorted to conservation in order to squeeze more people into our cities. And what that leads to is demand hardening, so that basically you've already used up your conservation capacity in order to be able to squeeze more people into your city. So then when you have a drought, since you've already used up that conservation capacity, you don't have as much conservation capacity in order to get through your drought. And one of the things that you'll see here is, and this is actually probably a good story, urban water use has actually gone down since 1995, despite our increasing population. Now, we normally think of that as a good story, but again, to the degree that we have done that, by reducing everyone's water use, that just makes it more difficult in the future to conserve water if you're in a period of drought. Similarly, another thing that concerns me is that if you drive up and down Highway 5 in the Central Valley of California, what you will see is that we are replacing the traditional row crops like cotton with permanent crops like vineyards or like fruit and nut trees. And the problem here is that, again, if one of our traditional methods of getting through a drought was that we would pay a farmer, for example, not to plant crops in a particular year and then transport that water to our urban areas, well, to the degree that we have permanent crops, that becomes more difficult to do. Because it's okay not to plant cotton in a particular year, particularly if the farmer's paid for that lost water. But to the degree that you have permanent crops, then it becomes more difficult to starve those crops of water because you're losing your capital if those particular crops die. So effectively another example of demand hardening. Another solution that I suggested earlier was you can draw on groundwater. Well, that's great if what you do is that you draw on your groundwater during the dry years, and then in the wet years you let the groundwater fill back up. And in some regions of the state, we're doing that. So for example, this green set up here of points is the Sacramento Valley groundwater aquifer. And what you'll see here is they go up generally during wet periods, they go down during dry periods, hopefully they go back up in the wet, then they go back down in the dry. And what you're hoping is that every time you get a wet period, you go back up to where you started at the beginning of the dry period. And in a lot of the state, we're managing our groundwater effectively. But look what we're doing in the Tulare Basin. We are, during a dry period, running it down. Then we run it down even more during the wet period, run it down in the dry period, run it down during the wet period, run it down during the dry period, and effectively what we are doing is using up that cushion of groundwater upon which we are reliant during the dry period when we really need that water, by basically utilizing that water even during periods of time when there is plenty of water in rivers to meet our demands. And then finally, I suggested that one of the ways in which we've met droughts in the past is that we have effectively robbed fish of some of their water. Well, that works if you're only doing it during some drought periods. But again, what we are doing in California in many of our rivers is that we're denying them water even during the wet periods. And furthermore, we have done other things such as harm their habitat, which puts them under the type of stress so that it's very difficult to further reduce the amount of water that they get during drought periods. And what this shows is the status of endemic California fish species. Since 1975, right before that 1976-77 drought. And at that point in time, 56% of our California fish species were stable. Another 44% were either extinct, they were listed on the Endangered Species Act, or they were considered vulnerable by biologists. Look, however, at where we were just 4 years ago. That point in time, we only had 17% of our fish species that were stable. Over 80% of all of our fish species were either extinct, listed under the Endangered Species Act, or imperiled. And that's an indication that we're not just robbing our fish of the water and habitat that they need during the dry periods, we're doing it during the wet periods also, which again makes it all the more difficult to turn to this buffer during droughts. So what should we be doing? Let me just suggest several things, and then I'll be happy to give you a whole variety of other ideas during the question and answer. One is that we should continue to focus on water markets. Water markets are a very effective way, again, of paying some people to conserve during periods of drought and then transferring the water to those areas that need the water the most. Our water markets in California, however, are still not particularly good. They're a lot better than they were 30 years ago, but it's still very difficult to actually move water around the state. So we actually have to open up our water markets so that they can be more effective during periods of drought. And some of you might know I actually wrote an editorial a couple of weeks ago where I suggested that fish should also be able to participate in water markets. And in particular, the idea was if we're going to take water from the fish in any case during periods of drought, shouldn't we pay the fish for that water? Shouldn't we pay money to the California Department of Fish and Wildlife for that water exactly at an equivalent rate that we would pay farmers, so that the Department of Fish and Wildlife would then have some money that they could use to restore habitat or take other actions that would help relieve that pressure that otherwise exists on our fish species. A second thing that I think is very important is we need to diversify our water supplies. Southern California has actually done a great job of diversifying its water supply. This is what's known as the Metropolitan Water District of Southern California and all of its various member agencies. And the Metropolitan Water District depends not only on its local water supplies, but also from the Colorado River, also from Owens Valley, which is way up here, and also from the State Water Project, which brings water down from Northern California. They also have groundwater banks, which I'll come back to and talk about in a moment, where they're storing water in groundwater aquifers for use. And they have all those storage facilities, which I mentioned earlier. Basically, they've taken a whole variety of actions so they're not simply relying upon one water supply in a period of drought. Probably a number of you have heard of the dozen or more communities in California which may fairly soon be without any water at all. All of those communities are relying upon one water supply. And to the degree that we can actually pull our water supplies together and tie them effectively together so that no one is relying upon just one source of supply, then again, it can help you get through a drought. I mentioned a moment ago the idea of storing water in groundwater aquifers. Historically, the way in which we've saved up water for dry periods is we've built reservoirs. Reservoirs have a variety of problems. They're expensive, they have evaporation, they're environmentally harmful in many cases. But as I mentioned a moment ago, we've actually mined a lot of our groundwater aquifers. So one thing that we can do is take water during wet periods and either through recharge ponds or various pumping operations store that water in underground aquifers. And then when we need that water in periods of drought, pump it back up. What this chart up here shows is the amount of water that we have stored in what are known as groundwater banks. Starting in 1994, as you can see, we have been making increasing uses of these groundwater banks over time. What's really interesting is if you look at the last major drought period that we had in California, which was in the middle of the last decade, we were able to draw very effectively from those groundwater banks. And then what we've done is we've begun to recharge them again. So this is a much more effective method than reservoirs, and one that we need to turn to more frequently. We also need to think about drought-tolerant sources of water supply, and my favorite is reclaimed water. Reclaimed water is economically competitive throughout virtually all of California, and we are not making anywhere close to as much use of recycled water as we might. This is a picture of the Ellis Creek Water Recycling Plant in Petaluma, which was recently completed. And there's no reason why by the time we have the next drought after this one, we can't have increased our amount of recycled water use by a factor of 5 or 10-fold in the state of California. So let me just close with the one thing that actually I'm not a big fan of, which is desalination at this particular point in time. And the desal plant that you see here is the Santa Barbara desal plant. Back in the 1986-1991 drought, Santa Barbara thought, okay, we need to have a drought-resistant source of water. And so what they did was that they decided that they were going to build a desal plant. It cost them $34 million to build this particular plant. And the year that they completed this plant, we had what were known as the Miracle March rains, which it sounds like we're not going to get this particular year, or probably not.
It would be a miracle, I guess.
It would be a miracle. And so they tested this desal plant, and then because they really didn't need it and it was really expensive, they put it in standby mode. And then when even that turned out to be pretty expensive, then they put it in long-term storage mode. They are right now thinking about whether or not they should open it back up, ramp it back up. As I mentioned, it costs $34 million to build. To reopen this plant, anyone have any guess? $20 million to reopen this particular plant. Even to simply put it back on standby mode would cost Santa Barbara $100,000 a year, even though they were not using it. Normal water supplies in Santa Barbara are actually relatively inexpensive. They're about $100 an acre foot. Much of Southern California is more in the $400, $450 an acre foot. This desalinated water would cost $1,500 an acre foot, which is the major reason why I do not think at the moment it's a really valuable way of dealing with the drought. And that $1,500 an acre foot doesn't take into account the cost of restarting this plant. If you take those costs into account, it's about $3,000 an acre foot. Plus, furthermore, and this is something people don't frequently think about, this particular desal plant is right by the ocean, right? I mean, that's where you want a desal plant. Santa Barbara depends largely upon gravity flow to get the water to people's homes. So even if they started up this plant, paid $3,000 an acre foot for the water, they then have to pump it uphill in order to put it into its water system so it then flows down to the homes. And this is highly pure water, and as a result of that, it also has other problems such as stripping minerals out of your pipes. Now, ultimately, desal is the solution, right? I mean, you know, if we run out of fresh water, there's lots of salt water out there to turn to. But given the cost and given environmental concerns, my own view is this is the last thing we turn to. So just in summary, what do we need to do in order to prepare for that future drought? We need to protect our existing flexibility by protecting our groundwater, protecting our environment during wet years, and preserving that water cushion, not hardening our demand too much. We have to expand on that particular flexibility immediately through greater use of groundwater storage facilities, water markets, diversifying everyone's supply, tying aqueducts throughout the state together so you can move water around more effectively, and turning to recycled water. And in the long term, but only in the long term, we can turn to desalination. And so with that, I'm going to hand things over to Tom so he can talk about the issues we face here at Stanford.
Okay, let's bring it home to Stanford. Kind of the atmospheric global view and then the statewide view, and then we'll look right here at what's going on at Stanford. I'm going to try to cover like a Stanford Water 101 real fast, so buckle up, here we go. All right, you kind of know where we are located, here on the southwest portion of the Bay Area. What you may not know or be as familiar with is that we are topographically located at the foothills of the Santa Cruz Mountains all the way down to this alluvial area where the campus is. And so that has some relevance for our water systems. Before we talk about our system specifically, we need to divide water up into various categories. So we need to look at our imported San Francisco water that we get. Most of our potable water comes from there. Our own local surface water, which comes from creeks. Because of Stanford's 8,000 acres spanning that huge distance topographically, we have creeks that run right alongside our campus, so we're fortunate that way. And of course, groundwater, we have our own wells. We do have a little recycled water system, and in the water that we don't want but want to get rid of, wastewater and storm drainage. Those categories of water split into various water systems. These are distinct, separate piped systems that we have at Stanford. First of all, what we call our domestic water, the water you use in your homes and in these buildings, is our potable water system. Next is our what we call lake water. You'll see why in a minute. That's non-potable. We use that primarily for irrigation. And then recycled water, sanitary sewer, of course, we all have to get rid of that waste, and then drainage for when it does rain, we have to get rid of that runoff. Here's the source of our pristine San Francisco Hetch Hetchy potable domestic water. These formations up in the top of the Sierra are pristine water supply. You might call it almost virgin water. That water travels all the way across the Central Valley and across and around the bay, all the way up the peninsula to San Francisco. And on the way there, it actually goes right through the Stanford campus. Through our foothills, we have these major San Francisco pipelines that we tap into through what are called turnouts, and fill our own reservoirs on the Stanford property with that potable water and feed our own campus by gravity from those reservoirs. We also have wells, which actually are a backup emergency potable water supply to the San Francisco system. They've spent $4 billion retrofitting that system to survive an earthquake. That's terrific, but just in case we get an earthquake bad enough to sever that line, we can still support what I consider my 13,000 dependent students here for potable water to continue with their lives. So that's our backup. Those wells are located here along San Francisco Creek in the west part of campus for the most part. There's another pipeline that goes through Palo Alto down El Camino that we can also backfeed the campus from. Here's a picture of one of our water storage reservoirs up in the foothills. This is Reservoir 2, 6 million gallons. And one of our water wells, well 3, this is the well right here with piping and all the electrical control panels and other appurtenances that you need for a well. So besides that potable system, I mentioned our creeks, and what we have are a number of creeks going adjacent to Stanford. San Francisco Creek coming along the north side from Searsville Reservoir, and Los Trancos Creek coming from the south. These join and become San Francisco right along the edge of campus. And this creek system provides a local surface supply for Stanford. And we actually developed a system pre-university days. Leland Stanford actually started these water systems by buying up the water rights and the facilities, a dam at Searsville, and Job Felt had built a dam and he rebuilt that. And we actually were able to procure our own surface water system, which is very unique. Most municipalities don't have a separate non-potable system with their own sources, so we're very fortunate that way. So here's the lake water system, as we call it, and now you know why we call it lake. Felt Reservoir is actually what we call an off-stream reservoir. Creeks don't flow into it, but we divert water from Los Trancos to Felt. And then Searsville is an in-stream reservoir. 4 creeks feed into Searsville, and it has a dam. Those impounded reservoir stored volumes of water are piped through this orange shown piping all the way down to the golf course and campus to provide irrigation water, and that's what we use it for, all for irrigation. We also have a pump station on San Francisco Creek that can lift water to those same pipelines. So here's a photo, aerial photo. We went on a little flight last year, that was kind of fun, of Searsville Reservoir. We actually have a real big study going on of Searsville because Searsville is 90% silted in. You can see the reservoir that remains, this open water body. This whole riparian forest area that I'm outlining is all built on sediment deposited in that area from primarily Corte Madera Creek, which is getting sediment from the foothills. The water body of Searsville used to extend through this whole area, and it's 90% silted in. It's about 14 feet deep at the dam, which is right here. What are we going to do with this facility? A myriad of engineering, hydrology, biology. We've got wetlands that are established, habitats that are formed, migratory birds, bats, you name it. We have all that to deal with in this very challenging problem. And some of you here are involved in that study with us, and we appreciate that, as is Buzz. This will be very complex. We hope to really delve into that study and get some real good recommendations put together for our management later this year. That's Searsville. Searsville, when it's spilling, and we hope it will be in just a couple of days, looks like this. Water coming into the reservoir is spilling right through the spillways of the dam and go on down to Corte Madera and then San Francisco Creek. Felt, on the other hand, lies out here in the middle of what looks like a desert. There are no creeks coming into Felt, but we divert water which comes down this flume and fills it. And there's Felt Dam right there. So here's the earthen dam at Felt Reservoir. Its intake tower, there's the reservoir. Felt is pretty low right now as well. We'll talk about where we stand with our water supplies in a minute. This is the facility that feeds Felt Lake. This is our diversion at Los Trancos. The dam is off to the right, and a few years ago we modified this facility and put in a long concrete, what we call a step pool and weir fish ladder. This is the creek down here, and fish actually come in this slot into this concrete channel, migrate all the way up to Los Trancos and spawn. Steelhead are one of these endangered fish species that Buzz alluded to. And I never thought as a civil engineer operating water facilities I would have to learn and get to know so much about biology and fish and habitats. That's the reality of doing water in California. This is our San Francisco Creek pump station down near the golf course. The pump station is here below the creek. This is the creek intakes. Pumps are down here, pump the water up these pipes into that same pipeline that goes all the way up to Felt and down to campus. So that's how we get that water. Our recycled water system is located right next to our central energy facility. It uses industrial process wastewater from our cooling tower system, which generates chilled water for the campus. And before that water is sewered, we actually intercept it, put it through microfiltration and disinfection, put it in this tank, and pump it through purple pipe to about 20 buildings on campus. Here's the plant here. School of Medicine has a couple new buildings. The buildings we're in right here, Science and Engineering Quad 2, and all the way down Sarah Street to the new Graduate School of Business. All these new buildings are dual plumbed with toilets that can take water in a separate system, and we're using that recycled water for that purpose. Okay, let's talk about water use. That's where we get it. How are we using it? In the 1960s, we, like many communities on the peninsula, didn't have San Francisco system. We had our own wells. So we were using wells, and as the campus continued to grow, had to meet that demand. Then Hetch Hetchy water came along, and we glommed onto it because it was terrific. We love that water. So everything went on Hetch Hetchy water, to the point where we were using so much of it that we approached our 3 million gallon per day allocation of San Francisco water. And this is way in the early 1980s. So we had to back off of that heavy use of that imported San Francisco water, and we put a lot of the irrigation areas like the golf course, athletic fields, back on our own non-potable lake water system, and decreased our San Francisco water use and got us back in the clear for a while. Then, about 10 or 15 years ago, we really began intensively to look at water conservation. And we have retrofitted fixtures all over this campus, to the point where our domestic water use has come down, even though our growth has continued. As a result of importing San Francisco water and getting off of using our wells as much as we had been year-round for potable water, we now just use them for non-potable, our groundwater supply actually has been able to replenish from the groundwater table being about 150 feet deep, back on up through a couple of decades to about 70 feet deep, and that's where it's stabilized. So our groundwater is in good shape. Okay, one thing we've done, I mentioned, is to convert a lot of our irrigation from potable water to this non-potable system. So in green, we can see the golf course, athletic fields for the most part, and much of the campus are irrigated with this non-potable water. That's the way we like it. There are still some areas that are in blue, domestic water irrigation, particularly this big area here, faculty staff housing. They're still irrigating their yards with potable water because they don't have a non-potable water system. Don't blame them. One of the next things we got to look at is getting non-potable water up to the faculty staff area so they can irrigate with the same non-potable water. That's where we are. So what's coming up? After all of that conservation, as Buzz mentioned, our conservation opportunities are a little tougher. We're hardened, you might say. So we got to look at other things we can do. One thing we can do is continue this conservation, and even though the campus is continuing to grow, stay for the next couple of decades below our allocation. But we have another sustainable activity going on campus right now in our energy field. Every 30 years or so, we build a new energy plant. We're building a new one right now. Instead of being a system that relies on cooling towers, this new plant will actually use a different system called heat recovery and not need near as much water to generate chilled water for the campus. It's going to reduce its water use, potable water use, by 70%, a net 18% reduction in the campus total potable water demand. So that's huge. And that will take us, that will lower the curve of use down even further and take us out a couple more decades until our growth eventually gets us up to that point. So from a potable water imported San Francisco standpoint, we're sitting pretty well with our long-term perspective. This energy plant is shown here. It's kind of west part of campus, back in the equestrian area. So you can see this big pasture. Under construction now. It's supposed to be coming online in just a little over a year. Not quite in time to solve our problems for this drought. Okay, let's talk a little bit about this conservation program. Marty Laporte and my group deserves a lot of credit for the last 15 years of decreasing our domestic water use by a tremendous amount. We keep track of our water use. Everything, almost everything, is metered. We know where it's going. We know who's using it. We know the types of uses, both for domestic water and for lake. For domestic, we have 4 major users: the academic campus and athletics buildings, student housing and dining, the central energy facility, and faculty staff housing. They each use about 1/4 of our total domestic water. We've done a little bit of retrofitting. Each of these dots represents a conservation efficiency water conservation project, and we've done many of them. We've spent a lot of money doing it. This is not cheap and it's not easy, but a lot of retrofitting's been done. To the point where, despite the growth of the campus, our domestic water use is down 500,000 gallons a day from about a decade ago. Here's a graph showing our declining domestic water use, now stabilized, and our pretty stable lake water use. A bit weather dependent, but that's hanging in there pretty stable as well. So if we look at sustainability, which is the mantra and the way we're operating, not only in energy but also in water, what do we need to look at? Our surface water, imported water, we have a long-term agreement with San Francisco that we signed a few years ago, so that's pretty well set. No increase in allocation from them, but at least that supply is set by contract till 2034. Groundwater, we're doing a tremendous amount of groundwater investigation to see how much more yield could we get. It's looking like about twice the level at which we're pumping now. We're still finishing all of that analysis. But that shows some promise for a bit of an increase if we need that. Local surface water supplies, Searsville, as I mentioned, is undergoing a huge study that will inform us about that aspect. Stormwater capture, we're already doing a little bit of that at Graduate School of Business. In our climate, that's tough because we get rain for so few months and none the other months that it's not like in the Midwest and back east. For every 3 or 4 days, you get more rain, fill up your tanks, and then irrigate again. We have to store all of it in a few months for use during the dry months, even in normal years. And that's a lot of storage, and storage costs a lot of money to build. But if there's a way to do it, eventually we'll need to look at that as well. And then recycled water, we actually are not only looking at industrial process wastewater, but our own domestic wastewater. As Buzz mentioned, the South Bay, Southern California, they're all doing it. Our concern is making sure that the pharmaceutical residuals, the personal care product residuals that we all use and discharge don't end up being used for irrigation to the point where we've got them accumulating in our groundwater supply. I happen to want to preserve our groundwater supply as a potable supply. So we need to do enough research that we make sure we have treatment processes that reliably deliver recycled water that we're not going to have concerns about or high risks of putting back into our natural environment. We actually have a project with Civil Environmental Engineering, so that's where the operations at Stanford and the academic side of Stanford kind of integrate, put their brains together, and try to come up with what can we do here to actually test some treatment processes that Perry McCarty is going to start with his experience on and doing, to see if we can come up with advanced treatment processes that will assure us of the increased level of treatment that we can reliably use it for these other purposes. So that's in the works. All of these facets of supply, along with ways we can minimize our demand, will come together in about the next year or two into a sustainable water management plan. We got to get these pieces figured out before we can put it all together. So the drought, that's why we're here. It has affected the Sierra snowpack. Even if we do get a little bit of rain in the next few days, maybe next month or two, it's not going to be enough to catch up to normal. So the snowpack is impacted. Obviously, our local creeks and reservoirs have too. In 15 years of operating our creek water diversion facilities, I've never gone to February 25 and not diverted a drop of water from our creeks until this year. This is a first. So we're using wells a lot more than we normally do for our irrigation. We have little runoff to capture, and of course, in the dry area season, irrigation demand goes up. That's fighting us all the way. What can we do? We've already done a lot. We got to look at ways to do more. We'll figure that out. The specifics are yet to come, but obviously we've shut off the fountains. They actually use a few thousand gallons a day, so it does count. It's not just a political statement, but that does matter. Even though they circulate their water, they have to change over, and we have a lot of fountains on campus, and so we've shut those off. But we have to look at all the ways we're using water to come up with the specifics of what we're going to do, and we'll be doing that over the next few weeks, and kind of roll out some specific measures. We have to talk to our colleagues, our customers in athletics, student housing, faculty, staff, the academic campus, grounds, to see where can you cut, what can you do, what can you do inside, what can you do outside, and put all these together in something that's realistic. To say we're just going to cut 10% without knowing some idea of how we're going to do that would not be very well thought through to do. So we're going to do that and take that effort. And we'll find the ways to do it. Mostly it's increasing efficiency, eliminating waste. Don't you hate it when you see those sprayers spraying onto the sidewalk, spraying onto the street? Why are we watering when it does rain? Why are we watering 4 or 5 times a week when we probably could water and keep it pretty green if we watered 2 or 3 times a week? If we get more efficient, we might not even have to sacrifice that much. But in case the drought does continue to prolong itself, and maybe even into next year, even though San Francisco's reservoirs are about 70% full, they're multi-year reservoirs, they're not getting replenished. We got to start preparing now for the next year in case this continues. As we've experienced, it has. What can we do to continue and accelerate our retrofits, to do what's left, to get those in place? And then if it gets worse and continues to hang on, we'll look at cutbacks. Where can we sacrifice lawns, the decorative lawns first? Where can we water less and eliminate that demand? So that's where we are with Stanford. I think we're in pretty good shape, but we've got a lot of work to do to weather this drought. I'm sure we will. Leon.
So we've got time for questions. I think we'll take them sitting down here. And just it's obvious to everybody we are taping the panel tonight. So if there's any parts of it that you want to rewatch or you want to pass the word on to somebody who wasn't here tonight, video will be posted on the Water in the West website, waterinthewest.stanford.edu in a few days, I think. So, questions? Sir.
This one's for Buzz. Buzz, you laid out a number of things that can be done from an infrastructure standpoint to improve the situation. What institutions actually are working on those? You have a laundry list, but didn't explain who gets them done or who's working on them, or is that somebody have to create somebody to do that?
Yeah, so the question from Tim was, I mentioned a variety of institution or technological changes that need to take place, and who is it that's actually responsible for achieving those? One of the things that you find in the water field is that you have responsibilities that stem all the way from the local level to the federal level. And basically all of those governmental levels have to be working on this particular issue. So for example, deciding on the amount of recycled water that we're going to be producing, that's generally a local issue. Increasing the amount of water market activity that we have by decreasing the transaction costs involved in trying to market water, that's generally going to be a state issue. But I actually see David Hayes back here, who's former Deputy Secretary of the Interior. If you're talking about marketing Federal Bureau of Reclamation water, then you have to have the Federal Bureau of Reclamation involved also. So this is one of those areas that has multiple levels of government, and all of them have to be involved in actually solving this type of an issue.
prospects of regulation of groundwater, should it be done at the state level? Can it be done locally?
Okay. So the question is, what about the prospect of regulating groundwater? So one thing that people should know at the outset, if you don't know it already, is that California really at this point in time is the only western state that does not have anything in the nature of statewide groundwater regulation. Texas comes close to being as unregulated as California, but at this point in time, I think we beat Texas.
They're trying harder.
They are true, yes. Or we're trying hard. Whichever. Yeah. Now, that doesn't mean that in California there aren't a lot of areas that are regulating their groundwater sustainably. There are a variety of regions in Southern California that, for example, are doing it. That's all being done at the local level. And you have a variety of local water districts that are doing, again, a very good job of trying to manage their groundwater sustainably. But unfortunately, we have areas like the Tulare Basin where that is not taking place. I think that there is a very good prospect that sometime within the next year or 2 years, we will see finally in the state of California a major effort to regulate groundwater at the state level. And my own preference would be that we regulate it by setting an overall standard at the state level that would basically provide that, over a period of time, you cannot mine your groundwater. And then you let the local districts decide how they're actually going to implement that. And if they don't implement it, then the state would step in. I think it's much more likely you're going to be able to get that type of regulation, because the last thing a lot of local groundwater users want is state regulation. And frequently at the local level, you have a lot of expertise, and you want to be able to use that expertise in figuring out how most effectively to manage that groundwater.
One of your slides showed that roughly 75% of the water consumption in the state is agricultural. We spend a lot of time with urban gyrations about how to save water, yet driving through the Central Valley, we see water-intensive crops and cattle. Isn't it a lot more efficient to attack that part of the problem?
Okay, so the question is, given that agriculture uses about 75% of the water in the state of California, isn't that where we should be focusing our
Well,
attention?
and also the inappropriate crops that are being grown, where obviously the value of water is not being reflected in the choice of crops.
Yeah, so the other question is, aren't we also growing a lot of crops that we shouldn't be growing? Okay, so there's a lot of different questions packed in to that one. First thing is, yes, we do need to be focused on trying to get even more water conservation in the agricultural sector than we've seen in the past. And if you looked at one of my slides that showed that urban water use has been going down, actually agricultural water use has been going down even more. So the agricultural users have actually been doing a pretty good job, and we shouldn't criticize them without recognizing some of the conservation that they've engaged in. I think the most effective way of getting that conservation is through water markets, where urban areas or other farmers that need the water pay those farmers who can do with less to actually reduce the amount of water that they're using. We could go in there and we could regulate them, but politically that's going to be a lot more difficult. And frequently they might not have the money to actually adopt those conservation measures. The other nice thing about markets, it gives the farmers the money then to actually engage in the conservation. Final thing is on the crops that we're growing in many areas of California. We still have crops that we shouldn't probably be growing in the state of California. Actually, from a purely water use standpoint, although I criticized earlier from a demand hardening standpoint our movement towards vineyards and trees, a lot of that is now micro irrigation, drip irrigation, and so it's actually not bad. And then other areas that I historically criticized all of the rice that we grow in California, but the truth of the matter is that we have destroyed 90% of the natural wetlands in the state of California. And so now with our migrating birds, when they look around for wetlands, they look at all of those rice farms. And the Nature Conservancy, as you may know, is now working with those rice farmers to get them to leave the water on their fields for a longer period of time. So it actually turns out to be effective habitat for the birds. And I mention all of this not in order to try to necessarily defend all of the rice that we're growing in California, but just to suggest, like everything else in the water field, it's complicated. And there's no necessarily easy answer.
No, so are you done?
I'm done.
So I was going to use the moderator's prerogative here, and I think it's been so long, everybody forgot that Daniel left us with a cliffhanger, which is how much rain the El Nino effect is likely to bring us next year. So I'm going to jump in, and I'm surprised nobody took you up on your cliffhanger, but I will.
All right. Well, I think a lot of people in the audience are probably familiar with the sort of the typical association, at least in the in the common view that El Nino is associated with heavy precipitation in California. And I think that one of the first plots that I showed, that time series of California precipitation, certainly reflects that some of the really big precipitation years in California are associated with those strong El Nino events. But I think that's where it gets slightly complicated, and it turns out that the majority of the relationship between California precipitation and El Nino comes from those strong events. So if you look only at weak to moderate El Nino events, the connection between precipitation and the sea surface temperatures in the eastern tropical Pacific aren't actually as strong. So to have a high confidence in a wetter winter, we'd need to have high confidence that El Nino would actually be pretty strong. And it's still far too early to make that kind of statement about what's going to happen next winter. I will say that those subsurface temperature anomalies in the western Pacific are analogous to the ones that we saw before the 1997-1998 El Nino. So they are of similar magnitude, which suggests at least the potential for a significant El Nino event if everything comes together next fall. So the one good thing I would say if El Nino ends up occurring of any strength is that it would probably disrupt this highly anomalous pattern of ridging over the North Pacific. So even if next winter isn't exceptionally wet, it seems fairly unlikely that it will be as dry as this past winter.
So we won't get the ridiculously resilient ridge redux.
Hopefully not, although maybe I'll have to come up with some other alliterative monkey there.
Can I actually ask one other question of Daniel, which I'm sure is one that you're frequently asked, which is, do we have any sense at all as to whether or not the R cubed is simply an anomaly that we will see every 30 or 40 years? Because if I remember, we saw something very similar in the 1976-77 drought. Or whether or not we think that it has any relationship to changes that we're seeing elsewhere around the world as a result of climate change.
Sure. And I'm sure that you're not the only person wondering that. So it's an interesting question. As you mentioned, actually, if I were to show a plot of that similar, that field where you can see the triple R most prominently in that geopotential height field with the big red region over the North Pacific, if I were to create that same plot and put it up there for 1976, 1977, you would see something similar for at least part of the winter. It wasn't quite as strong and it wasn't quite as persistent then as it has been this year. But that is the kind of pattern that we tend to associate with extreme dry spells in California. Obviously, the current one is the superlative one in the historical record. But that spatial pattern of anomalies is what we tend to associate with droughts in California. In terms of the broader climate question, that's actually something that I'm working on right now, and we are taking a look at what the sort of the probability of occurrence of this event is, sort of characterizing it in the present climate, and then asking the question of how likely was it in a climate before greenhouse warming. And so at some point, hopefully, we'll be able to actually give a quantitative answer to the question of, is this event more likely now than it was in the past, or will this event become more likely to occur in the future? And I think generally that's a difficult question to answer because California lies in sort of an unusual region, climatologically speaking, in the sense that we're sort of on the margin of where a lot of the climate models that we use to make projections for the future, we're sort of in that zone where some of the models think it might get wetter and some of the models think it might get drier. But even that doesn't necessarily answer the question about drought, because even if we hypothetically were to become wetter in the future, you could conceivably see an increase in variability or an increase in the intensity of droughts. In fact, even that's a fairly robust expectation in the sense that those droughts that do occur will probably be more intense, partly because temperatures on average will be warmer in the background. So it's a complicated question, and hopefully I can give you a better answer in a few months.
So another cliffhanger.
Another cliffhanger, I guess, yeah.
So in the back of the room there, you've been patiently waiting.
I'm curious about the impact that the drought's going to have on energy prices and energy supply and demand at the same time, and was wondering both how that interacts at the micro level at Stanford and at the...
So the question is about how the drought will interact with energy production and energy demand at the micro level at Stanford and elsewhere.
And I'll confess, I don't have a good answer to that question. I mean, obviously, we will produce less hydroelectric energy as a result. And in fact, another concern I've always had with desal is that desal is very high on energy use. And so if you rely upon desal in cases of the drought, then you need the desal water at exactly the point in time when you have less electricity because it's drier. And so, you know, I think there's a lot of very interesting issues there, but I actually do not know, and somebody else in the room might, whether or not the current drought is having any impact on the actual price of electricity. Anyone want to raise their hand and tell the answer? No. Okay.
Well, let's answer that question. Maybe soon, in the last couple of weeks, there was an article in the Weekly on how much more power was going to cost Palo Alto because of less hydro. But my question was, Tom, in Palo Alto, we can get rebates from the Santa Clara Valley Water District and from the city of Palo Alto for pervious pavement and changing out lawns. I haven't driven around factory staff housing, as you know, but is there like a requirement that people have front lawns?
I'll tell you right now, I do not have a front lawn, so it's not a requirement.
Tricia's question has to do with rebates from the Santa Clara Valley Water District as well as Palo Alto on retrofits to decrease irrigation demand for lawn by taking out lawn, that kind of thing. Much of the campus lies in Santa Clara County, so the water district's rebates could apply to our folks as well. Our faculty, staff, residents lease Stanford land, and they own their houses, so it's a little different. They're not really property owners, but that program still could exist. As we look through all of these measures and the kinds of things that we want to initiate and accelerate in terms of water use reduction, that question and what rebating we might do at Stanford for people to do that, along with the water district's rebates, as well as people have brought up the use of gray water. That's come up as a possibility. There are, of course, concerns about something you can't control like gray water. But as we look at the myriad of measures that are possible, we'll formulate kind of our policies about that for Stanford folks as well.
But that's,
oh, I'm sorry.
I just wanted to sort of add to that. I mean, it's a really important question, though, as to how you actually go about providing incentives to people to reduce their water use. When I first moved here, like 25 years ago, we did not meter water on the Stanford campus. Once we started metering water, I think water use in the faculty ghetto fell by about a third at that point in time. We're still not doing some things, though, that I think we should. I think tiered pricing systems, where if you're a larger water user, those last gallons of water cost you a lot more. I think that's a really effective incentive system. A lot of cities are using that effectively. And then the other thing, which a lot of us get in our energy bills from PG&E, is that little indicator that shows how much energy we're using compared to our neighbors and compared to our really efficient neighbors. And it turns out that that has a huge impact on how much energy people use. And I know here on the Stanford campus, we've been playing around and looking at various ways of providing that type of information to people.
That's right, we have. In fact, the more people know about their energy and water use, the more careful they are about it. We've started kind of a pilot program on not necessarily tiered rates, because we could get some resistance to changing how much your bill is for your water. But on knowing how much water you use, putting on a device that actually doesn't just tell you how much water you used the last month, but how much water you used last night or 15 minutes ago, real-time ability to read your water use. It's real interesting when people call our hotline, our water hotline, and say, my water meter was going at 2 in the morning, and I know I didn't have the kitchen sink or bathtub going. So we go and they've got a leak. They didn't even know they had a leak, but we can check that kind of thing out. That's the kind of more efficiency, increasing efficiency, waste reduction movements we can make. They really don't cost a whole lot, but really have a pretty good return on the investment for those kind of meters and making that information available online.
So we got a question here and a question here, so I've got.
Okay, quick question based on some work that asked here before and something you said. You described the complexity of the whole system. Given that, and given the likelihood of future droughts, what is your ideal, in an ideal universe, if everybody put in the right kind of policy, how much more would water cost, both the municipal user, us, and the agriculturalists?
You know, so the question was, you know, if we had sort of an ideal system, how much more would the water cost? And so I'll answer this carefully because I've actually never done the calculations. But in my view, you not only charge full cost for the water, both in the urban and the agricultural areas. So you put in all those various costs. My own view is that you also charge on a marginal basis to the larger users. Right now, most places just have an average cost. They take all of the costs, they divide it by the total amount of gallons, and that's how much you get charged. My view is that person who's using that last water, they should get charged however much it's costing to bring in those last gallons of water, and frequently those are much more expensive than the first gallons of water. And then the third thing, very controversial, I would charge to the degree we could, the cost of the impact to the environment of actually taking that water out of our rivers and streams so that people have an incentive to leave that water in the rivers and streams where it's important to do so.
So the price per gallon would be full cost, baseline cost which is now heavily subsidized, use for the last few gallons and use for the environment.
That's right. And my guess is that would mean that those folks at that last gallon, I'm just guessing, but I would imagine something in the nature of 4 or 5 times maybe what they're being charged right now. But recognize, I mean, I don't know if any of you have compared all your various bills recently, but my guess is your water bill is less than your energy bill. My guess is, unless you have a huge front lawn, and my guess is that your water bill is less than your cell phone bill. Water is cheap, right? And the only reason why we get upset when people talk about raising the price is because we like the status quo. We don't like anyone telling us they're going to raise the price.
Yes, thank you for your
Are
patience.
there political limitations on relying upon the markets? The markets price assumes that you have a commodity to distribute, and whereas we might choose not to employ in the future, we cannot choose not to drink water. When these communities, in the same manner, start going to drought, it's inconceivable that there won't be very heavy pressure from the federal government and the state government to step in and do something. So there's a farmer who says, well, I could maybe
make my operation more water efficient, but I choose not to do it. Besides, you haven't given me enough money to do it. So it may be the basis of an infrastructure project that goes far beyond anything that's been discussed on that. So I'm really pointing to the political imperative that when people get punched in bellows, then they come out of the streets like nothing we've ever seen before.
Yeah. So the question is, if we rely upon markets to gain water, doesn't that risk the possibility the water is going to be so expensive that there are going to be cities that wouldn't be able to afford the water? So several things. First of all, if you actually look at how expensive various sources of water have been over like the last 10 years, water markets turn out to be actually a very effective price. So less than recycled water, certainly less than desalinated water. The second thing is that I believe that whatever policies we have, we obviously have to have a policy that ensures that everyone have an adequate amount of water at a price that they can afford, which is actually another reason why I believe in a tiered pricing system, in that I would basically have a lifeline price for a basic amount of water so that everyone is able to afford that basic amount. And then what you do is you charge the guy down the road or the woman down the road that just loves that green lawn and swimming pool, and you charge them a lot for that water. And that's fine because it encourages them to save water and they can afford it. But I do think you obviously have to worry about that.
Yeah, so the number that I saw this week, which I'd seen before, was that per capita water use in California for municipal water, San Francisco is about 70 gallons a day, and Palm Springs is north of 700 gallons a day. That's per capita. So
it costs more to water your lawn though in a desert.
Yeah.
Is that a clarifying question about desalination? When we're talking, when you say desalination, you mean desalination always of seawater, not just brackish wastewater? Because as I understood, there's a different energy cost depending on what water source you're using.
So the question was, the costs that I was quoting were those costs for desalinating ocean water and not brackish water. And a really important point here is that frequently when we talk about desal, we're talking about taking salt water from the oceans and desalinating it for example, urban use. Another area in which we use desalinated water is that we have a lot of brackish groundwater. Groundwater that is high in salt content, and in order to be able to use it, we also have to remove that salt. That desalination of brackish water is significantly cheaper, and it is something that not only do I think we should do, but we actually do throughout much of the United States. Just one little quick trivia question. The country in the world that uses the most desalinated water? Saudi Arabia, very good. The country that uses the second most? United States. And that's because of all of the brackish water that we desalinate. We're actually the second largest user of desalination technology. So let me just suggest for a moment, because I love talking. That's why I became a professor. But why don't we, a couple of questions first for either of the guys at either end here, and then we can sneak in on this.
Question for Stanford. Yeah. If the dam ever has to be taken down, how much water, normal water, goes into Stanford?
Okay. The question was, if we took Searsville Dam, assume you mean, down, what would that do to our non-potable supply from that source? We're now getting about 400 acre-feet the last several years from the Searsville part of the system. And there are ways we are looking at to replace that somewhere else in the system. So it wouldn't be that we have to give it up just because we lose the dam. But that does have to be considered and factored in as to the decision.
let's take one or two more, and then there was a.
So I live on a cattle ranch in the Spruce Valley.
Yeah.
We've gotten less than an inch this year. And if we're expecting these trends to continue to become more extreme, do you see something that happened in the 19th century with the Southern California cattle ranchers happening in this really dry region? And I'm just personally curious.
Yeah. I'm looking over, I'm seeing whether or not Daniel would answer the question.
Well, I think that, I guess there's two components to that question. One is what's going on meteorologically with the actual precipitation. The other is what the response of the cattle ranchers might be, and what the sort of the human response to the the changing climate is. And I can't necessarily speak so much to the second part directly, but I think that the water use in California, as I think we've heard about tonight, is a function both of what falls from the sky, what we can retain in reservoirs either above ground or in groundwater, and how efficient we are in using that. And so the part we really can't control is the rainfall, and potentially in a certain sense, in a very large scale, we have some influence on it, but we can't directly control it. And so I would say, since we don't know exactly what the future holds, especially in terms of these extreme events, in terms of these extreme dry events and these droughts, I think it's an open question, sort of what the response to that might be, other than to say that if we have some inclination that the severity of existing droughts will be higher in the future, and that's something the people will have to plan for.
It seems to suggest, because agriculture with crops, you can control a bit of that supply through storage, while cattle ranching on a large scale without a big water source that you're irrigating or doing some Australian sprouting methods that they're doing, is going to be much more climate sort of restricted.
Yeah, no, you're the most vulnerable out there, right? About the only thing in addition to the things you just talked about is you could buy hay.
Which we're doing, but it's not something you're going to be doing in any sort of long-term.
Absolutely right. Yeah, so you're the most vulnerable. So I would imagine that the cattle industry would be the first to go, presumably as a result of a drought. So, sorry about that.
Well, I'm sorry. I know people have other questions, but I think it's probably time to wind down. So I'd say a couple quick things. Again, if you anybody who wasn't here, recommend that they watch the video on the website. The other thing I'll say is I hope not to see you all again here next year.
For this topic.
But thank you very much for coming. And if the drought does persist through next year, I promise I'll see you all again in a larger room. But thank you all for coming and cramming into the room. It was a terrific evening. Thanks for all your great questions, and another round of applause for our great panel.